Today we're going to talk about reflecting waves. Alright, imagine I have a string and it's fixed at one end. For example, imagine I have a guitar string and the string comes to the bridge. It goes over the bridge and it's pinned down so it can't move there. This is a fixed end. The string cannot move. Alright, so if I have the end of my string is at x equals L, then the displacement of our string at location L at any time will always be equal to 0. Or maybe I have a string fixed at the x equals 0 end. Then y evaluated at x equals 0 at any time has to equal 0. That's what a fixed end is. Alright? Now what happens if I have a pulse or some wave coming along moving towards my fixed end? What happens when that wave hits the fixed end? Alright? Well, I could imagine, alright, the way I'm going to think about this is I'm going to imagine that my string doesn't end here. I'm going to imagine that my string goes on. And I have a wave coming from the other direction that looks like this, alright? So I have my incident wave, it's going the other way, but it's flipped upside down. As these two waves come together at the middle, they will cancel each other out, and this point will not move, alright? So now I have a situation where I'm obeying the same wave equation over here, I'm obeying my boundary condition, the string is fixed, alright? So I ought to get equivalent results. So what does that tell me? If I fix a string at one end, the wave that comes back will be the same wave that went in, but it'll be traveling backwards and upside down. It'll have the same amplitude, carry the same power. None of the wave is absorbed, but it comes back upside down. Now let's consider a free end. What is a free end? It turns out, in short, a free end is an end in which, rather than having the displacement always be 0, we're going to set the derivative equal to 0. So the derivative of y with respect to x at x equals 0 at any time has to equal 0. So we're going to make sure that the string is flat at the end. Alright, your book gives kind of a convoluted, weird example where they say, imagine you have a string and it's tied to a massless ring sliding on a frictionless pole. Alright? And they say, okay, the pole and the ring can support forces going this way, right? But if I have my string coming off this way, if there's any upward component of force, my ring is free to move upward, but F equals ma, my ring has no mass. If there's finite force, it will have infinite acceleration. Therefore, my ring's going to move infinitely fast to prevent us from ever having an upward component of force. All right? That's the book's kind of convoluted thing they want you to think about. All right? When we talk about sound waves, we will find a much more natural places where free ends occur naturally, like at the end of an organ pipe. Another way you can think about this is imagine I have a thick string, like a rope, and I tie it to a very thin string, alright? So going from the thick rope to the thin string, in the limit as my thin string has 0 linear mass density, we end up with a free end, alright? And the slope, it can move up and down, right? But the slope always has to be 0 as it comes into that end. Now what happens if a pulse comes to a free end? Alright, and like I say, this is going to be important when we get to acoustics. We're going to say, I've got some wave traveling down an organ pipe, it hits a free end, what's going to happen? We're going to do the same thing. We're going to imagine that our string goes on and that there's some wave coming the other direction. Alright? So this is supposed to be the same wave but flipped around. Alright? The point is here, where this wave has a negative slope, this one has a positive slope, and so although the string will move up and down, these two waves will not cancel each other out, their derivatives will cancel. So what does that tell us? If I have a free end, my reflection is going to come straight back. It's going to look like my original pulse, but just turned around, and it will not be inverted. So with a fixed end, I get inversion. With a free end, I don't. All right? Again, all the power is reflected. The amplitude is the same. It turns out that those are the two limiting cases where I get total reflection, when I have a fixed end or a free end. Now let's talk about something in between. All right? So let's imagine we have a junction. Let's consider a string joined to another string with a different linear mass density. Now this is analogous to a lot of different things we see in everyday life. For example, electrical signals traveling in cables. If the properties of the cable change at some place, you're going to get reflections there. When I was in graduate school, the most common way to wire up computers to the internet was using coaxial cable. And instead of having a separate cable for each computer, you'd have a cable that comes from the wall to your computer, then you'd daisy chain go to the next computer, to the next computer, and the next computer, and so on. The problem with that is if somebody unplugs a cable, suddenly you have a place where the wave properties, the properties of the wave medium change, and you get reflections. and that messes up the internet for everybody. Imagine now light going from air into glass. The light can continue to propagate into the glass, right? It's not the end of the wave medium, it's just a change in the properties of the wave medium. Why do you get reflections off of the glass? Well, because whenever the velocity of a wave changes, at that point you'll get reflections, as we're going to see with our string example. So we're going to solve for a string, but the equations are also good for light reflecting off of glass. Another thing that this affects, bells on instruments. Why does a trumpet have a bell? Why does a trombone or a saxophone or a clarinet or a French horn or a tuba have a bell? Well, it turns out the velocity of waves inside of a tube is slightly different than the velocity of sound waves in free air. So at the end of your trumpet, you've got this tube. If it just comes to a sudden end, there's a sudden change in the properties of the waves and the speed that the waves travel in the medium, and you get reflections. Now you want reflections in a musical instrument because you need to set up resonance, as we're going to discuss on another day. But you don't want that reflection to be too strong, or not much of the sound will couple out of your instrument and it won't sound loud. So the bell of an instrument is designed to change the properties of the wave medium in a more gradual way so that less reflection occurs. All right, so let's consider our two strings joined together and know that it's important for a lot of different things. Now, we're only going to consider sine waves reflecting at this junction and transmitting at this junction, because it turns out that every wave you could ever write can be written as a sum of sine waves. We're going to talk about that in another day. But the basic point is, if you can understand what a sine wave does at our junction, you can use that to figure out what happens with any arbitrary wave when it hits your junction. Okay, so we've got this incident wave coming in. So the incident wave or incoming wave, that's our given. We're sending this wave in. We want to know what happens when that wave hits the junction. What will the transmitted wave look like? In particular, will it be at the same frequency? All right, here's an illustration that shows why not. I'm going to have a sine wave on the left and a sine wave on the right, and they're going to be oscillating at different frequencies. Note what happens in the middle. All right? The two ends start together, but they break apart. They're oscillating at different frequencies. So if the two waves oscillate at a different frequency, our string breaks. So the first thing we note is that the transmitted wave has to be at the same frequency. All right? So maybe it just changes wavelength and moves on. Why would this transmitted wave be at a different wavelength? Well, remember, the velocity of a wave is it travels one wavelength per period, and 1 over the period is the frequency, right? So velocity is wavelength times frequency. If the velocity of our wave medium changes, but the frequency of the wave doesn't change as it goes through, that means that the wavelength must change, right? In particular, if I take the velocity of the waves on the incident side, that's the wavelength of the incident side times the frequency. The velocity of the wave on the transmitted side is the wavelength on the transmitted side times the frequency, and the frequency is the same on both sides, right? We already decided that. If I take the ratio of these two equations, I find that the ratio of the velocities is equal to the ratio of the wavelengths, or 1 over the ratio of the wave numbers. So we're going to be using sine waves, and for simplicity, we're going to write them in terms of the wave numbers. Remember, k sub I, that's the wave number of the incident wave, that's a given. We can figure out what the wave number of the transmitted wave is by comparing the velocities of the two strings, right? And presumably the two strings have the same tension, but they have different linear mass densities. If we find the ratio of the velocities of the waves on those two strings, we can find the ratio of the wave numbers. So given the incident wave number, we can find the wave number on the transmitted string. Okay, so here's our assumption. Okay, so this is all good and well. But let's think about this assumption right here, that the wave just changes wavelength and moves on. Here's what you get. So I have a sine wave on the left, a sine wave on the right. They both have the same amplitude, they have the same frequency, but I've changed the wave number, or the wavelength, of one of them. Notice the string doesn't break, that's good, but there's a little cusp. Can you see there's just kind of a little point right there at the middle where they join? Right where they join, you have something where you have this wave coming here, and then suddenly the slope changes. And you have this cusp, right? We zoom in on that cusp. Boom. All right? If we look right here, as I zoom in on that cusp, as I get smaller and smaller in the limit of an infinitely big zoom in, I have a point here with no mass. But I have net force on it because I have tension pointing that way and tension pointing that way. They're pointing in different ways, so they don't totally cancel each other out. Zero mass, finite force, infinite acceleration. So what we're going to decide then is we can't have that cusp. So the slope must be continuous as I go from one string to another. All right, so here's what we know. The string can't break, and there can be no force on that point where they join, which means that the slope has to be continuous. So what really happens? I'm going to get, it turns out that just having transmission cannot satisfy those two boundary conditions, that the string can't break and the slope has to be continuous. So it turns out I need an extra term. So in addition to an incident wave and a transmitted wave, I will also have a reflected wave. So on the left side, here's my incident wave. I'm given some amplitude. It's assigned with some frequency. With that frequency, I know what, depending on the properties of the string, I know what the wave number is, all right, and it's traveling to the right, the minus sign right here. So this is the given wave, and I want to know what happens to that wave when it hits the junction. Well, part of what happens is it reflects back. So on the left string, I'll have the incident wave, but I'll also have a left-going reflected wave. What its amplitude is, I don't know. I'm going to have to figure that out. It may have a phase shift, phi sub r. I don't know what that phase shift is. I'm going to have to figure that out. All right? On the right-hand side, I'm going to have a transmitted wave. I don't know what its amplitude is. I don't know what its phase shift is. It's traveling to the right. All right? So I'm going to take these two equations, and I have some unknowns, the amplitudes and phases of the reflected and transmitted waves. And I'm going to use those boundary conditions to see if I can figure out what those constants need to be in terms of my given constants. Now notice, in the book, most of our sine waves are kx minus omega t, and here I have omega t minus kx. It all works, all right? You can write waves that way. This is still a wave traveling to the right. This is one traveling to the left. It just, for our derivation, it works out cleaner if I put the omega t first, all right? Ki is the wavelength, the 2 pi over the wavelength on the left side. Kt, k transmitted, is 2 pi over the wavelength in the right side on the second street, all right? Okay, and then what conditions must hold at the boundary? We're going to let our boundary be x equals 0 for simplicity. We'll define it to be x equals 0. What has to be true? At x equals 0, these two displacements have to be the same. These two things, right? The two ends of the string have to track together. It can't break. And the slope of these with respect to x also have to be the same. All right? So those are our two boundary conditions. Okay, so here we go. What we're going to do, first of all, let me just say, if we just assume right off the bat that these phase shifts are 0, this problem works out really easily. All right? But maybe you didn't think to try that. That's something we do in physics, is we try an easy solution and see if it works. And if it doesn't, then we go back and try the harder one. So we might just say, hey, let's just set those two to 0, see if it works. If it doesn't, we'll come back and try the harder problem. And it turns out it does work and it's simple. But let's not do that. Let's say we didn't think to do that. I've got these sine waves with all this garbage in there. I'm going to get the garbage out by using complex exponentials. So I'm going to write a complex representation of my waves. So y tilde left is something that if I take the imaginary part of it, I get y left. And y tilde right is something that if I take the imaginary part of it, I get y right, okay? And all I've done is I've taken the sine waves and I've turned them into complex exponentials, all right? So let's apply our first boundary condition. Our first boundary condition was this evaluated at x equals 0 has to equal this evaluated at x equals 0. So at x equals 0, this is just ai e to the I omega t, and x is 0, right? And then we have plus ar e to the I omega t, kix, that goes to 0 because x is equal to 0, and then we have I phi. But I'm going to do this trick where I'm going to take e to the I phi and absorb it into my constant and make a complex amplitude, so I don't have to keep pulling that phase shift around with me. All right, that's phi sub r. On the other side, I've got at e to the I omega t. This part goes to 0, and again, I'm going to take e to the I phi t and combine it with this constant right here and call it my complex amplitude, a tilde sub t. All right? These cancel out, and I'm left with ai plus ar tilde is equal to a transmitted tilde. All right? Now I have to set the derivatives equal to each other at x equals 0. When I take the derivative with respect to x, what comes down, right? What happens? I take my derivative of my exponential, the exponential remains unchanged, but I take the derivative of what's inside, and here I'm going to bring down a minus ki. So minus ki ai, all right, times this thing evaluated at x equals 0 is just e to the I omega t, plus, and then here when I take the derivative with respect to x, my exponential stays the same, but I'm going to pull down an I ki. So plus, oh, I left off my I here, plus I k incident, a reflected, e to the I omega t, the x part goes to 0, and I'm going to absorb my phi into my complex amplitude, right? And then I take the derivative on the right, I'm going to bring down a minus I k transmitted I've got A transmitted tilde. The x goes away, we absorb that, so it's just e to the I omega t. The e to the I omega t's cancel out, the i's cancel out, and I'm just left with negative k incident, A incident, plus k incident, A reflected tilde, is equal to negative k transmitted, A transmitted tilde. All right? So now I really have two equations for unknowns, right? I don't know the amplitude and the phase for the reflected and the transmitted parts. But I'm kind of pretending like this complex amplitude is just one thing, so I can sort of think of it as two equations, two unknowns, go through and solve them, see if I get an answer. And it turns out you can. You just substitute things in, solve two equations, two unknowns, and it turns out that what you get in the result after doing the algebra is this right here. All right, so these are the expressions you get. And you look at them, and there is nothing complex in here. This is all real, this is all real. So we determine that this is also equal to our real amplitude, right, A reflected, and this is equal to our real amplitude, A transmitted, and phi transmitted equals 0, and phi reflected equals 0. Okay, so we get our answer. Now we're basically done, right? I send in my sine wave. I know all the properties of the sine wave that's reflected. I know all the properties of the sine wave that's transmitted. All right? You can go through and calculate the power in the reflected and transmitted waves and prove to yourself that it's equal to the power coming in. Energy is conserved. All right? But let's look at this. In the limit, as I have a really, really, really heavy string, second string, right? So I take my string and I'm tying it to a rope, and I make that rope bigger and bigger until it's a wall, all right? Remember, the velocity of a wave is the square root of tension over mu. This is tension now, not period, right? So the tension is the same. If I take the linear mass density and make it go to infinity, all right? So, right, so I'm going from a string to basically a wall, right? If mu goes to infinity, the velocity of my wave goes to 0. If my velocity of my wave goes to 0, remember, v is equal to lambda f. If the velocity of my wave goes to 0, that means that the wavelength at a constant frequency has to go to 0, which means the wave number goes to infinity. So if I'm going to a wall, kt is infinity, right? In the limit as kt goes to infinity, k sub I is insignificant, and I'm just left with this over this, and I just get a -1. So A reflected is minus A incident. Hey, when I go to a wall, I'm supposed to get the same wave back with the same amplitude, but upside down. That's exactly what I get, right? What if, instead of going to a wall, what if I go to an infinitely thin string? That's supposed to be like a free end, right? Well, in the limit as I go to an infinitely thin string, right, my velocity goes to infinity. Infinite velocity, fixed frequency, means my wavelength has to go to infinity or my wave number goes to 0. So if kt goes to 0, then I'm left with just k over ki, I get 1. So my reflected wave has the same amplitude as the incident wave, and it is not inverted. All right, so we see just what we saw before in those limiting cases in our answer right here. So that gives us some hope that our answer is correct. There's another limiting case that I know the answer to. What if the two ropes have the two strings have the same linear mass density? Then there was no end. My wave should just go through. I should have no reflected wave, and my transmitted wave should just look like the incident wave, right? Well, if the velocity is the same, the wavelengths are the same, these two cancel each other out, I get no reflected wave. And here I have 2 times ki, but ki and kt are the same thing, so it's just 2 times ki divided by 2 times ki, and I just get a transmitted wave going through. So, you know, it looks like we have an answer that's doing something reasonable. Let's see what happens when I plug in some numbers. Here's an example of what if the velocity on the transmitted side is half the velocity of the incident side. All right? I plug those numbers in, and this is what you get. Notice I've got a transmitted wave on the right, and its wavelength is shorter than the incident wavelength on the left. Also notice on the left, the wave is kind of throbbing up and down. Why is it doing that? Well, because there's not just an incident sine wave, there's also a reflected wave going back that's canceling with it and making it, adding and subtracting to it, depending on whether they overlap or don't overlap at a particular time. It's making that wave kind of throb. All right? Notice at the middle, the wave doesn't, the two strings don't split, and the slope is continuous across the middle. If we zoom in on the middle at different times, you can see at all these different times, the slope is continuous. Our answer seems to be working. It fits our boundary conditions. Now let's do the opposite. Let's go from a low velocity to a high velocity, so that the velocity on the transmitted side is twice the velocity on the incident side. This is what you get. All right, we still have kind of a throbbing wave, and it looks like our boundary conditions are still met. Everything is happy. Okay, so it looks like this works. Once again, velocity equals 0. We plug it in. We already analyzed this in our head. Let's do it with the computer. The velocity of the transmitted wave is 0. That's like going from a string to a wall, and we get this. All right, waves reflected back, no transmitted wave. What if the velocity of the transmitted wave is infinity? That's like going from a rope to a string. That's like the free end. And again, all right, the fact that this throbbing wave, both in this case and in this case, the fact that it goes all the way to 0, and we get what we call as a standing wave, we're going to talk about that later, means that the amplitude of the incident and the reflected waves are the same, so that the reflected wave at certain times, when things overlap just right, it can totally cancel out the incident wave. Notice, for our free end scenario, the slope at the end of our string is 0. For the fixed end, the displacement is 0. And that's all I've got for you today.